All right, everybody. In this video, we're going to try and quickly go through 11.3. It's going to teach us about the chi-squared test for independence. So we learned about the chi-squared distribution in the last video. You know, it's this right-skewed distribution, and we learned how to use it to perform the goodness of fit test, which I believe they've actually snuck one of those in here in the notes on us. Here is another thing we can do with the chi-squared distribution. We could use it to test for independence, okay, between two categorical variables. So it looks to see if things are associated. So when we talk about independence, what we mean is independence. What that means is that the two things are not related. No association or no connection. If we say that two things are connected, we would be saying they are dependent on one another. So these, they do have a relation. They are connected. They are associated. And so, for example, take a look at what we're going to look at here. We're going to look at in this example, and what they're going to do is they're going to use this example to walk us through the 5 steps of performing this test. Okay, and a lot of the steps are very similar to what we've already learned. They are basically comparing whether or not getting a cold, right, or fighting off a cold, I guess, is related or independent or dependent on taking echinacea. So we want to see, is there a link between taking a supplement of echinacea and getting a cold or not getting a cold? In other words, does it work, or should we not bother? Okay, so this is what we're going to go through, and let's make sure we understand what the table is showing us. Is you've got people that got a cold, and you got people that did not get a cold in this little medical experiment here. And for this group of people, they took a placebo pill. So their pill had 0% echinacea. All right, now this group of folks took a pill that contained 20% echinacea, and then this group took a pill that contained 60% echinacea extract. And so again, we want to see is, does it look like as people took more echinacea that fewer people got the cold? And I mean, here you could look, there's 103 people total there. 15 were able to avoid a cold, so 15 out of 103. So that's 14%, just to get an idea of what we're talking about. It's 14.6%, but let's look at this group. There's 52 people there, and 10 got a cold. That's 19.2%. So comparing the two groups here, the people that took no echinacea supplements and the people that took 60% echinacea extract supplement, you could see that more people here did not get a cold, right? More people were able to avoid the cold by taking echinacea. Now, is that just because of this particular sample? You know, samples vary all over the place, so is this just normal fluctuation we expect to see in our sample? Or is this statistically significant and there is actually a benefit to taking echinacea? All right, we need the statistics to figure that out for us. So that's exactly what this test does, the test for independence. We look to see if two things are independent of one another. In other words, are they not related, not connected, or not associated? By the way, this is always the null. This is always the null hypothesis when you're doing this test. We assume that there is no connection, and maybe if we reject the null, we will say, no, I think there is a connection. Okay, so let's just walk through the process of how to do this, and then there's 2 other examples in the notes, and we will we'll be done. So again, I hope you got the idea of what's going on. We're going to compare the effectiveness of taking echinacea compared to whether or not you get a cold. So step 1 is always the same. What is your hypothesis? Okay. So again, the null is always that they are independent, that there is no relationship, that getting a cold is independent or not related to the treatment group. In other words, getting a cold has no bearing on which group you belong in, whether you got the placebo pill or the 60% extract pill. There's no relation. The alternative to that would be, well, no, there is a relation. Getting a cold is dependent on which group you're in. In other words, maybe we find that we're less likely to get a cold if you're in that group. Okay. My alpha, I'll take good old 5% since it doesn't tell me. All right. So again, I want to see if there is a link between getting a cold and taking echinacea or not. Step 2 is the same. It's name the test. This test is called the chi-squared test for independence. Now the requirements, step 3 is always check IRL. Okay, independent, random, and large. Well, let's just kind of do these real quick. I'm just going to abbreviate them. Independent. I didn't add up how many people we're talking about here, but it looks like under 300, maybe 200 or 250. It is definitely less than 5% of everybody that gets a cold, right? It's definitely less than 5% of the population. So I'm just going to say yes, less than 5% of the population. And I'm being very lazy with it, so don't do this on a test. On a test, I would write it out thoroughly and elaborate. At least count them up and tell me how many people you got here. Random, you know, it doesn't say, but if it's a clinical trial, you know they're putting some efforts into doing a good experiment. So I'm just going to write doesn't say, but I'm sure any clinical trial takes that into account. And then large enough. Now remember, large enough is different for almost everything every type of distribution you're working with, right? Or every type of test statistic you're working with. For sample means, you need at least 30 data values. For sample proportions, you need the number of successes and fails to be at least 10. We just learned in the last video that for a chi-squared test statistic, you need the number of expected frequency values to be at least 5, okay? So we need to figure out the number of expected frequency values. Now, how the heck do you do that? That's new. So let me just write that down right here. So we need expected counts to be at least 5. In other words, I need to make sure that when I run this experiment, that what I would expect to get is at least 5 in each category. Each of these categories. Now this is what I actually got. These are my observed values, right? So that's not what they're talking about. They're talking about, well, what would you expect? Here's how you find it, okay? To find the expected count, right, for a two-way table. All right, you first find the marginal frequencies, and what the marginal frequencies are the row and column totals. And then you calculate the expected frequency by taking the row total times the column total divided by the grand total. And that will give you the expected frequency in that particular column. Let me show you how to do it. It's really not bad, okay? But again, just to kind of remind you though, these were the observed values. Let's over here write out my expected values. And so I'm going to draw a grid, and the categories are going to be the same. So right here, this was got cold, no cold. This is 0% echinacea. This was a 20% echinacea pill, and this was a 60% echinacea pill. So what I need to first calculate are the marginal frequencies. I need to figure out the grand totals for each column and row. So if I just add all these up along the side here, 88 plus 48 plus 42, I get 178. So I'm just going to write the totals here. And if I add all these up, that's 39. And so my grand total down there is 217. So here's a row total and another row total, and here's my grand total. I need to do the same for the columns. So we said this column had a 108 in it, or I'm sorry, 103. If I add down, I get 103 people in this category. This would be 62 people in this category, and this would be 52. And to make sure I did it right, I'm going to add them all up, and I should get 217. Yep. So there's our grand total. So, all right, so that's kind of the weird part. That's finding the marginal frequencies. What does each row and each column add up to, and what is the grand total? And now to find the expected value, I'm doing this right here. I'm taking the row total times the column total divided by the grand total. So if I want this box, I want the expected value of this box. Okay, this box lands in the got a cold but had 0% echinacea. Got a cold, 0% echinacea. So I need to find the row total for got a cold and the column total for echinacea, for 0 echinacea, and divide it by the grand total. So the column total for got a cold is here, 178. I need to multiply by the column total for 0% echinacea. That was 103. And I need to divide by the grand total, 217. Okay, it's weird. It's not hard, it's just time consuming. That would give me an expected value of 84.5. That would be my expected value there. I'll do another one. Let's just find, how about this expected value here, just to kind of jump for one. This hole is in the no cold column, and it is in the no cold row and the 20% column. So what I need to do is I need to multiply those totals. What's the total in the no cold row? No cold row had a total of 39, right? The 20% column, what was that guy's total? The 20% column had a total of 62. And divide by the grand total of 217. Let's see what we get there. I got 11.1. 11.1 here. That is the expected value for that column, or for that little box, right? For the no cold at 20%. And I would have to do this for all of these boxes, okay? I would have to take the row total times the column total divided by the grand total, and that would be the expected amount. Not hard, but it is kind of a pain in the butt to do. Anyways, take my advice for it. If we did all these, we're going to get at least 5, okay? We need these to be at least 5. So let's just say we got it. This is another reason why StatCrunch is nice, because StatCrunch will do this for us. It'll quickly calculate those totals for us, and we don't even have to worry about it. You know, one place we're actually going to need these is if you're doing it by hand when it comes time to do the test statistics. So that's where we're at now. We're at step 4. They didn't label it, but step 4, isn't that always find the test statistic and the p-value? Okay, so the test statistic, we already know how to find chi-squared. Remember, it's what you observe minus what you expect. You square it, you divide by what you expect, and that's one contribution. So I need to find the contribution for this guy getting a cold and no echinacea, this guy getting a cold and 20% echinacea, and so far. I will have 6 contributions that I need to add all of them together to get chi-squared. Okay, so I'll just maybe write out one. I'm not going to do all of them because I didn't bother to find all the expecteds, but let's say I want to find the expected value, the contribution from this first box here, from 0% and getting a cold, because that value I have. So what I observe is 88. What I expect is 84.5. I square that and divide by what I expect, and that's the first contribution. That is the contribution to chi-squared from the got cold and 0% echinacea box for that particular category. Now I'm going to have to do it for all the other boxes as well. Okay, and all those added together will give you your chi-squared distribution, your chi-squared test statistic. And so remember, what we're finding is we're finding some chi-squared value, and we are interested in the area to the right of that because we're always interested in. Remember, chi-squared tells us kind of how far we are away from what we expect. So the more to the right chi-squared goes, the more off our observations are from the what we expect to find. Okay, and this p-value, this area here, is the probability of doing that. Hi, one sec. Okay, I'm back. So where was I? Oh, we were talking about the contributions here. Okay. So all those together will add up and give me my test statistic, and then I'm just going to consult the chi-squared table because my p-value then would be the probability of getting a test statistic greater than whatever the heck that number is. Okay. Now, we learned that when reading a chi-squared table, that it's based on the degrees of freedom you have. Well, it's a little bit trickier in this one. The degrees of freedom in the goodness of fit test was simply one less than the number of categories you have. Here, the degrees of freedom is one less than the number of rows you have times one less than the number of columns that you have. Okay, so that's another thing that's a little different. I know this test might feel a little overwhelming, but it's just one of those things that you keep the procedure in front of you and you go through a couple times. You learn how to type it into StatCrunch and it's going to be a breeze for you. Okay, because really I wouldn't do these by hand if I were you, because it's a pain in the butt to have to crank out all these values. And this is for a small table. Imagine for a really large table. It's just not practical. So let me go ahead and pull up StatCrunch, because right now we're at the point where I need to find my test statistic and p-value and make my conclusion. So I want to do all that with StatCrunch. I'm going to pause the video real quick and get that all loaded up for you. Okay, one sec. Okay, I'm back. Let me flip over to StatCrunch and show you how to run this test, the chi-squared test for independence. So let's go to StatCrunch. So I've already loaded up the data for us, and so what you need to do is I've got 3 columns here showing my percentage of echinacea, and I've got 2 rows, one for those that got a cold and one that, for those that did not get a cold. Okay. Now I'm including those 2 categories in a column because I'm going to be, you'll see that we are going to be assigning that inside the test, and it's going to help with when it displays our results. Okay. So again, I just put that I have got a cold and did not get a cold, right? Those are the things we're trying to compare here, and I want to see if it helped to have these various levels of echinacea. Okay, now where you get this is not as obvious as the other tests. Maybe you're saying none of them are obvious, but here you actually need to go to a table and contingency, because what we have here is known as a two-way contingency table. Okay, so go to table, contingency, and you've got a summary. We don't actually have the raw data itself. That would be like a list 217 long with the data values. We have a summary of the data. All right, so it wants to know what columns is my data contained in. My data is contained in the 0%, 20%, and 60% columns. So I'm going to say those are the columns that contain my data. And then here's where it's asking me, okay, what column contains the labeling for the rows? So the row labels can be found in the column called variable 1, right? I didn't change that name, but that's where I put the labels for each rows. Here you can choose what you want the test to display. I think it helps to look at expected count and contributions to the chi-square. There's a lot you could look at. You don't have to look at any. I mean, ultimately you need the test statistic and the p-value. So if you just leave these blank and do it, that's what you'll get. But I think it's good to see these as well. So let's compute the thing. Oh, this test is the chi-squared test for independence. You just leave it where it's set. You don't need to worry about the other ones. Just more tests. And here's what it tells us. So here are the results, and they tell you the format. The first number is the count, so what we observed. The second number is the expected count, what we would expect, right? And so, and then the last number is the contribution to the chi-squared test statistic. So for the 0% echinacea people that got a cold, we observed 88. We expected 84.49, and the contribution is 0.15. So I think we did that one by hand. Let me see. Yeah, see, we did that one by hand, and I rounded the expected value to 84.5, and there's our contribution. So if we were to put that contribution into the calculator, according to StatCrunch, that's all going to come out to about 0.15. It's the contribution for that first category. Okay, so didn't we do another one of these? Yeah, here for the no cold 20% one, we found the expected value to be 11.1, just rounding. No cold 20%, it's 11.14. Okay, so again, I just rounded it. And 0.73 would be its contribution to chi-squared. The reason it's nice to look at the contribution is if you notice that there is an association, right? Like there is some link. You can then kind of sort of pinpoint a little more which one made the biggest impact on that chi-squared test statistic. So in other words, which one pushed it further to the right and maybe had the most impact on it. Anyways, ultimately what we needed is my chi-squared value. That's the test statistic from adding up all the contributions. Really didn't even need that. What I really needed is tell me the p-value. That tells me, you know, I compare that to alpha, and that tells me what to do with my test. So again, that's a little confusing, but you'll go to tables, and what you have is a contingency table. So I'm going to go to tables, contingency with summary, and then again, you're going to tell it where the data lives. You're going to tell it where the row labels are, and hit enter. And look, on this one I didn't select the other features, so all it did was gave me the totals and my p-value and test statistic. So let's see, 1.76 and 0.414. So this was 1.76 and this was 0.4146. All right. So last step, I know this has been a long 5-step process, but the last one is always to just write up your conclusion, right? So since the p-value is 0. Oops, how about they're looking for larger is greater than 5%, we reject, nope, we do not reject, we fail to reject the null. All right. Remember, if our p-value, we only reject the null if the p-value is below alpha. This is well above alpha, if I copied it right. Yep. And so we fail to reject the null here. If we fail to reject the null, it means we do not get rid of the null. It basically means that we accept it, that we say, well, there's no reason to think the status quo has changed, so we think that getting a cold is independent of the treatment group. Remember, independent means there's no relation, no connection, or no association. So based on this data, there is insufficient evidence to show that echinacea and getting colds are dependent, that they rely on one another. This has turned into a very colorful test, and it's all over the place. Again, I think it's one of those things you do a couple of them and they start feeling a lot better, okay? I want to skip this next test for a second, the next question, and let's go to the last one, and we'll come back to this. So let's go to this last one. So let's take a look at this example. It says that a random sample of 760 subjects was obtained, and each was tested for left-hand writing. Results are in the table below. Use a 5% significance level to test the claim that left-handedness is independent of gender. All right, so they looked at a bunch of males and a bunch of females, and they asked, who writes with your left hand? And so we had 23 males that wrote with their left hand, 65 females wrote with their left hand. So let's just walk through the steps. Let's walk through the steps. We'll do some of this by hand, but I definitely just want to use StatCrunch. So again, step 1, here they've lumped 1 and 2 together. So let's define the parameters, state the level of significance, and name the test. So step 1 is, what is the parameters? What are the hypotheses? All right, so the null hypotheses would be, remember, the null is always assumed that there is no relationship, that there's no relationship between the gender and whether or not you write with your left hand. The status quo is that there is no link, which that means they're independent. So the null would be that gender and being left-handed are independent of one another. Okay. The alternative to that is that they are not independent, that there is some sort of link between male or female being left-handed. Okay. So the alternative is that they are dependent, that there is an association. Again, I think I prefer the word not associated and associated. So you could use those. They said go ahead and let alpha equal 5%. They told me that. And then step 2 would be to name the test. Okay. And so again, this test is called the chi-squared test for independence. Chi-square test for independence. All right. Check the requirements and explain clearly. Okay, well, let's say independent. Do we meet that requirement? I don't know how many people we're talking about here. Let's actually find these column and row totals because I'm going to need that. So let's find these totals. So if I just add across the board here, this would be all the males. There's 240 males. This looks like 520 females. And so together the grand total would be 760 people would be the grand total there. If I add the number of people that, yes, they are left-handed, that looks like 88. And no left-handed, that would be 672. Okay, so again, I'm just adding down each column and adding across each row. And again, these two should add up to 760, which looks like they do. All right, so if I wanted to, again, remember, this is what I observe. If I want to find what I would expect, so again, I've got male, female. This would be yes left-handed, no left-handed, right? The way you find each of these expected values, again, you take the row column times the row total times the column total and divide by the grand total. So the row total for males is 240. The column total for left-handed is 88. And the grand total is 760. So I would multiply and divide 240 times 88 divided by 760. I expect out of this group to get 27.8 left-handed folks. I'm sorry, males that are left-handed. That would be my expected value. and I would need to do that for all 4 of these categories. I think I'm going to resist the urge to do it, and I'm going to let StatCrunch do it for me. Okay, but it's doable. The reason I wanted to start cranking out these numbers is I could use the 5% rule here. Definitely 760 is less than 5% of all people, all males and females, so treat as independent. Okay, are we random? Yep, I see it says yes, a random sample was used. And okay, sorry, I had to pause it there for a sec. So I think we were on large enough. And again, large enough, what we mean is we need the expected values to all be greater than or equal, or greater than 5, right? And so here we found one of the expected values. We got 27.8. I would have to go calculate the other expected values, and hopefully they're all bigger than 5. So often I end up just going to step 4 because I'm using StatCrunch, so I'm going to let StatCrunch figure those out for me, and then I'll come back to step 3 to verify. So I'm just going to write it now so I don't forget, but I will come back and verify that all expected values are greater than 5. So we'll come back and verify that. Okay. Now let's talk about the calculations. If I were to do step 4, that would be, first thing is go find the test statistic. So remember, for the test statistic, chi-squared is equal to the sum of all of these contributions. For each category, what did you observe minus what did you expect, square it, and divide it by what you expected. And then you add all of those up. So I would have 4 contributions here, right? One for each of these groups. Males that are left-handed, males that are not, females that are left-handed, and females that are not. So I'll just write out the first one since we went ahead and found it. I would take the one column, or the one group I did was left-handed males. So we said we observed 23 of them. We observed 23. We expected 27.8, right, according to what we did up here. And then I'll divide by what we expected out of that group. So that would be the contribution for left-handed males. And then, of course, I would need for non-left-handed males, left-handed females, non-left-handed females. We would need to find each contribution. Well, we're going to let StatCrunch do it for us, and then we'll also take the p-value it says, and I'm going to use it to verify that we did indeed have enough expected value. Let me pause it while I go ahead and load it all up, okay, and then I'll come back and share it with you. Okay, I've got the data loaded onto StatCrunch, so let me share that with you now. Again, what I did is I just uploaded this table right here, or I made this table on StatCrunch. Let's take a look at it. So again, I've got the left-handed column, the number of left-handed folks and non-left-handed folks, and I've got the 2 row labels, the males and the females. And so the way we do one of these tests for independence, again, is we are dealing with a 2-way contingency table. So you go under Table, Contingency, and again, I have a summary of my data. Data in this case would look like 760 different data values. That's not what I've got. I've got a summary. So again, it wants to know what columns are your data in. My data are in the left-handed and the non-left-handed columns. They want to know what column contains the labeling for your rows. So I put the labels male and female in that first column, variable 1. I do want to see the expected count because I need to verify that the large enough requirement has been met. And I'm going to go ahead and also look at the contributions just for the heck of it. And it's a chi-squared test for independence. Let's see what we get. So again, the way this reads, the first number you see is the observed count. So those are the numbers in the table here. The next number is the computer calculated for us the expected count of each one, right? We did this one by hand, 27 point something, and we found that. And then the third number is the individual contribution. So that first contribution we set up on OneNote, this guy right here, all right, this would come out to be, what? Let's see, the expected was 27.8. That whole thing would come out to be 0.83 would be that contribution. And so here's the expected for the non-left-handed males, the expected number of left-handed females, and the expected number of non-left-handed females, and there's their contributions. So that's just info to see. What we really need ultimately is what's my p-value, right? That tells me do I reject or fail to reject. So here's my chi-squared statistic, right? 1.36, and there's my p-value, 0.243, I'll round it to. 1.36 and 0.243. 1.36, 0.243? Yeah. Okay. So those are brought to us by StatCrunch. All right, and so my conclusion, well, looking at the p-value, remember, I only reject the null if the p-value is below my alpha. Okay, because again, the idea here is that if the null is true, if there truly is no association between gender and being left-handed, then the likelihood that I would get the data I got is a 24% chance for me to get that. There's a 24% chance that I would get this type of data if there really is no link between left and right-handedness and gender. Thank you. So that's not that unlikely, right? That's not out of the ordinary or that abnormal. So in other words, we do not think the null is wrong. I do not reject the null. We stick with the status quo that there appears to be no association between them. Okay, so let's write that up. Since our p-value is greater than alpha, we fail to reject the null. The data does not suggest the alternative. In other words, it doesn't suggest that there is a link or an association between your gender and whether or not you're left-handed. It does not suggest a relation between your gender and being left-handed. Okay. Now, again, I know in the beginning it's daunting looking at all these things. Realize running the test itself is easy. You can do the test in a minute because you put the table in, go to contingency tables, and tell it to do the test, and it's going to give you your p-value. So it can truly be performed quickly. It's the write-up and the procedure that just takes some time to get used to. Like all of the tests we've done, it's very systematic and routine, and there's no difference from this test and the next time you use it. The numbers will change, but you will be doing the exact same 5 steps over and over and over and over again. Okay, so I hope this one's feeling all right. I want to back up to the problem I skipped. Let's do that real quick and then be done with this. So let me go back. The reason I skipped it is because they kind of snuck this one in here. This is a chi-squared distribution, but this is not a test for independence. Let's read it real quick. It says that records of randomly selected births were obtained and categorized according to the day of the week that they occurred. And this is based on data from the National Center for Health Statistics. Because babies are unfamiliar with our schedule of weekdays, a reasonable claim is that births occur on different days with an equal. Let me try that again. A reasonable claim is that births occur on the different days with equal frequency. In other words, since babies don't know what day it is, we should kind of expect to see the same number of births on Sunday and Monday and Tuesday and Wednesday and Thursday. There's no reason to think that it would favor one day or the other. At least that's the claim, okay? So think about this for a second, and I've said it a long time ago. I think when we first got into testing, doing these tests, I think one of the hardest things in statistics is reading a scenario and being able to recognize, oh, that's the chi-squared goodness of fit test, or oh, that's the chi-squared test for independence, or oh, that's a two proportion z test, whatever. That takes some skill. You really got to know the criteria for those in order to be able to quickly decide on, oh, that's the test I should use. Once you know what test to use, then you're kind of home free. It's not going to take you long. But what this problem is talking about is it's talking about a distribution, and it's seeing whether or not a particular distribution is as claimed. So that's the goodness of fit test, right? That's like back to the M&Ms thing, saying M&Ms says there's this percentage of each color. Let's see if that's what happened in our bag of M&Ms. Here the claim is babies don't know what day they're being born, so the percentage of babies born on Sunday, Monday, Tuesday, Wednesday, and so forth should be all the same. It should be the same percentage of kids born on those days. All right? So this is actually a goodness of fit test. It's not comparing two different variables and seeing if there is a link between them. Okay? It is just saying that I think there should be an even distribution among all the days in which kids are born. So let's, and again, that's tricky and really takes some practice, and stick with it and you'll be all right. The good news is, our exam 3 and our final focuses on chapter 8 and 9, or 10 if you want to go into there, which I think you're probably have got a brown or black belt in by now. Okay. So the null hypothesis, again, remember with the goodness of fit test, let me get to that. The null hypothesis would be up here in this thing, and it says a reasonable claim is that the births occur on different days with equal frequencies. In other words, the percentage of births on Sunday, or the proportion of births on Sunday, should be the same as the proportion of births on Monday, which should be the same as the proportion of births that happen on Tuesday, and all the way down to Saturday. That they should see the same proportion of births, whatever that would be. The alternative to that is that at least one of those is wrong. Okay, at least one of the proportions is different. And again, it's not singling out a particular day, and we're not saying I think Monday has the most births. That would be a different test, right? That would be back to like a one proportion test. Here we're just going to say either they are all the same as we think the claim is, or they're not all the same. One of them is different. At least one is different. They don't specify. Oh, no, they do specify. Let alpha be 1%. So alpha is going to be 1% here. And then they also cram in step 2 into here. So step 2 is name the test. This is a chi-square goodness of fit test. All right. Let's check our requirements. If you add up all the births we have here, let me just verify. I have a total of 773 births. Well, definitely that's less than 5% of all births that take place, right? Okay, so 773 is less than 5% of all births. So we could treat as independent. Random, does it say random? Randomly selected, so yes. A random sample was taken. Now, are we large enough? Remember, that means the expected values have to all be at least 5. So let's think about this. This is what I observed. Let me see if I can cram in here what I expect. I've got 773 births, and truly, if what we expect is that they would be equally or evenly distributed, then I'm just going to take 773 and divide it by 7 days. That would be 110.428 or 43 births per day. They're all the same. Okay, and so we definitely have enough. We have all expected values are more than 5. All right, so we're good to go there. So let's run the test. Again, what I would technically need to do is, if I want the chi-squared test statistic, I would need to find everybody's contribution. So I would find the contribution from Sunday. And so from Sunday, remember, the contribution would be what I observe minus what I expect, square it over what you expect. Right? That is the contribution from Sunday. Right? Because, yeah, 77 births on Sunday. And now I need the contribution for Monday and for Tuesday and all the way down to Saturday. So it's doable. It's just a pain in the butt. It's tedious. So let's let StatCrunch give it to us and the p-value. So I'm going to pause this, load up the data for you, and then I'll pull it back up. 1 minute. Okay, let's go for it. Let's look on StatCrunch. So if I open it up, what I did is I loaded my observed values for each day: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Those were the observed number of births for each day. Now, I could plug in the expected, 110.43 for each of them. I could do it relatively easy, copy and paste it all the way down, okay? But if you remember, on the goodness of fit test, there's also the feature to just click the button that says all the expected values are the same, that there's an equal distribution of these things. And that's what our assumption is that they are equally distributed. So if you recall, I go to Stat. This is a goodness of fit test using the chi-squared distribution. My observed values come out of the column that I labeled as observed. The expected values come out of, well, if you put them into the expected value, then that's what I would tell it. I would say, look in that expected value. It doesn't offer it because there's no data in there. But again, since everybody is equally distributed, or I think it is, or that's our claim, that we can just hit this button that says all these cells are in equal proportion, and it's going to take that total of 773 and divide it by 7 for us. And let's see what we get out of here. So first of all, you see that it does crank out the expected value for each one. They're all the same. It tells you your chi-squared value, and it tells you the p-value. I'm curious, can I see, is that all I've got, my options? I was hoping it would maybe show me the contributions, but I don't see that option here. Kind of curious which one might have pushed it around more than the others. Anyways, that's what I need, is my p-value, right? So my chi-squared is 16.9, let's say, and 0.0097. 16.9 and 0.0097. All right, so that is from StatCrunch. So what does that mean, right? My p-value is 0.0097. That is well under my level of significance. It's actually not well under, it's just under because we used a very small level of significance here. But it is less, so that means I am going to, sorry guys, let me close my door. Okay, sorry, screaming kids in the background. P-value is less than alpha, so we are going to reject the null. Right, so since our p-value is less than alpha, we reject the null. The null assumed that there was an equal distribution of births on each day. It turns out that doesn't seem to be the case. It doesn't seem like it's equal. It seems like at least one of those proportions is different. So one of them is higher or lower than the rest, or more than one, but at least one of them is off. They're not all the same. So the data suggests let's see. Births are not equally spread out among the days of the week. Let's say that. Births are not equally spread out over the days of the week. Okay? So again, this one was sort of tricky. They snuck in a goodness of fit test here. And truly that's one of the challenges of statistics and the hardest part, I think, is trying to figure out what test to use. Once you know the test, you're kind of set because you have a strict guideline to follow. Okay, that's it for that one. Talk to you guys later.